let's review some rules for simplifying radicals. When using the quadratic formula, oftentimes you'll end up with an expression that needs to be simplified that may have a radical. For example, let's look at the expression 4 plus or minus the square root of 8. So we want to look at this radical and decide whether or not we can do any further simplifying with this expression. So just thinking about how radicals work, when we think about the number 8, the factors that make up 8, we could think of it as 2 times 4, and 4 is 2 times 2. So another way of thinking about 8 is that 8 is 2 to the third power. When we're simplifying radicals, we're looking for any pairs of factors that we can pull out. So with 8, we have a pair of 2's and then also a leftover 2. So the reason that pairs are important is if you think about the square root of 2 squared, a square root and a square are inverse operations and they cancel each other out. So the square root of 2 squared is just 2, which is why the square root of 4, since 2 squared is equal to 4, is equal to just 2. So when we're thinking about the square root of 8, if we think about this as 2 squared times 2, we can even think of those as individual square roots, the square root of 2 squared times the square root of 2. So this one simplifies to just 2, but then the other stays just as the square root of 2. So a lot of times when we're looking at something like the square root of 8, just kind of as scratch work, we'll say, okay, think of 8 as 4 times 2. So we're thinking about those factors that live on the inside. And so really we're saying this is equal to the square root of 4 times the square root of 2. So the square root of 4 simplifies to just 2, and then the other factor of 2 stays inside. Since it's not a pair, it doesn't have another factor to go with. So our original problem then, 4 plus or minus the square root of 8, we could simplify that to 4 plus or minus 2 square root of 2. Let's compare that to a couple more examples. Say that we had the square root of 90. So thinking about perfect squares that live inside of 90, we know that 90 is 9 times 10. We could do the same thing and think about the factor tree to really kind of emphasize this idea of pairs. That 90, if we think of it as 9 times 10, 9 is 3 times 3, 10 is 2 times 5. So if we break 90 down into its prime factors, the only pair of factors is 3 times 3. So that pair of factors is what's going to get to come outside of the radical. The 2 and the 5 are not pairs of factors, so they're going to have to stay on the inside. So if we think of the square root of 90 as the square root of 9 times the square root of 10, that 9 as a 3 squared is going to simplify to just 3, but the square root of 10, that factor, the 2 and the 5 are still on the inside. And so these are left on the inside. This 3 squared is what got to come to the outside. On the outside it becomes just a 3. One last example to just kind of close this out. Sometimes when we're simplifying with our quadratic formula, we will end up with problems like 10 plus or minus the square root of 75 all over 5. So we would start by simplifying the radical. Think of 75 as 25 times 3. So that 25 is a perfect square. It's a 5 squared, or a 5 times 5. So this becomes 10 plus or minus the 25 from the inside. Square root of 25 is 5, but the 3 is left behind inside the square root all over 5. We now want to simplify this further, remembering that each of those terms on top is being divided by that 5 on the bottom. So 10 divided by 5 is 2. The 5 on the outside is going to reduce with the 5 in the denominator, so this becomes plus or minus the square root of 3. So when you're working with radicals, we're looking for those perfect squares where it's a factor times itself. That is what's going to get to come onto the outside of the radical, and then anything that is not a paired factor is going to stay on the inside.